density or radiation density. Radiation power density or radiation density. It is indicated with the symbol W, radiation. So the radiation power density is given by half into real of E cross H star. Radiation power density is given by half into real of E cross H star. We know that this is also nothing but a average power. Average power. So power, therefore total power or power radiated. Total power radiated. Total power radiated is given by total power radiated. P radiation is equal to integration of power density or integration of power average, because both are equal. For an isotropic radiator, so we can assume a sphere. So isotropic radiator means a sphere which radiates equal in all directions. So this power radiation is given by total area is 4 pi r square omega radiation or W radiation, power density. Therefore power density is given by total power radiated by 4 pi r square. 4 pi r square for a isotropic radiator. So the next characteristic is radiation intensity. Radiation intensity of an antenna. It is indicated with the symbol U. So this radiation intensity is defined as U is equal to R square into power density, radiation power density. So that is also equal to R square into average power. So for a isotropic radiator, this is indicated with the symbol U0, because since isotropic radiator is a reference one. So I am indicating with radiation intensity of a isotropic radiator by U0 is equal to R square into power radiated by 4 pi R square. So R square cancels out. Therefore radiation intensity is power radiated by 4 pi. Power radiated by 4 pi. Next important characteristic is directivity. Directivity. So before defining this directivity, first of all we will define a directive gain. The directive gain is defined as directive gain dc is equal to radiation intensity of the antenna by radiation intensity of reference antenna, that is isotropic radiator. So this is nothing but U by U0 already we know, that is nothing but power radiated by 4 pi. Power radiated by 4 pi. Therefore directive gain of an antenna is given by 4 pi into radiation intensity by power radiated. So this directivity meaning is, physical meaning is, this is nothing but the gain in a particular direction. The gain in a particular direction. So dc is equal to 4 pi into radiation intensity by power radiated. So here directivity is the value of maximum directive gain. Value of maximum directive gain. So this directivity is indicated with symbol D0 is equal to 4 pi into U maximum by power radiated. U maximum by power radiated. This is the directivity definition or directivity equation. Here some important points regarding this directivity and directive gain are both directivity and directive gain are dimensionless. So there is no dimension for these two. The second one is for an isotropic source, both directivity and directive gain are unity. So for isotropic radiator, both the directivity and directive gain are unity, because for a isotropic radiator, maximum radiation intensity is nothing but power radiated by 4 pi. If you substitute that value, both will cancel. So radiation intensity is maximum for isotropic radiator. So that's why both the directivity and the directive gain are unity for isotropic radiator. Generally directivity is greater than 1. Generally the directivity value is greater than 1. This is except for isotropic radiator. Suppose for Hertzian dipole, for example, if you consider, for Hertzian dipole, directivity is 1.5. For lambda by 2 dipole, that is half wave dipole. For half wave dipole, directivity is given by 1.64. So these are general practical values of directivity. So that generally directivity is greater than 1. But directivity is unity for isotropic radiator. So another way of defining directivity is also defined as 4 pi by sigma A, or this is equal to 4 pi by sigma is nothing but beam solid angle. How we can define this beam solid angle is, it is nothing but, or it is defined as the solid angle through which all the power of the antenna would flow. So the angle through which all the power of the antenna would flow is defined as beam solid angle. It is indicated with the symbol sigma A, that is given by theta 1r into theta 2r, where theta 1r is half power beamwidth in one plane. The unit is in terms of radians. Similarly, theta 2r is half power beamwidth in a plane perpendicular to other plane. That is, it is a second plane which is perpendicular to the first one. The unit is also in radians. Therefore, directivity is 4 pi by theta 1r into theta 2r. This is also given by 4 pi by theta 1d into theta 2d into 180 by pi whole square directivity, where theta 1d and theta 2d are half power beam widths in degrees. So these two formulas are important. In the examination, they will give this half power beam widths in two different planes. Then they will ask what is the directivity of the antenna. So directly we can calculate by using these formulas. So next important characteristic is power gain. Power gain G. So this power gain is defined as G. G is equal to power radiated by power input. Power radiated by power input. That is, suppose this is the antenna. So what is the power in and what is the total power radiated? So total power radiated by power input is defined as power gain of the antenna. Power gain of the antenna. So this radiation efficiency. So radiation efficiency we already defined. Radiation efficiency already we defined eta R. Eta R is equal to, it is we defined as radiation resistance by radiation resistance plus R loss. It is also equal to power radiated by power input. The radiation efficiency also defined as power radiated by power input. For many antennas, power gain is approximately equal to directive gain. Power gain is approximately equal to directive gain. So directivity in dB is defined as D0 dB is defined as 10 log base 10 D0. Similarly, gain in dB is defined as 10 log base 10 G. So this is in terms of dB, both the directivity and gain. We will work out a problem based on this concept, what we discussed. Determine the electric field intensity at a distance of 10 kilometers from an antenna having a directive gain of 5 dB and radiating a total power of 20 kilowatts. So this type of questions are very important. Here they are asking, the solution to this problem is, so determine electric field intensity at a distance of 10 kilometers from an antenna having a directive gain. So suppose this is an antenna radiating some power having a the directive gain is 5 dB. So directive gain is 5 dB. So at a distance of, from the antenna at a distance of 10 kilometers, what is the electric field intensity? What is the electric field intensity? So directivity is given 5 dB. So just first convert into normal value. So this is nothing but 10 log base 10 directivity is equal to 5 dB. So if you simplify this, directivity is given by 3.162. Directivity is given by 3.162 if you simplify or if you convert into normal value. And another given thing is distance is given, that is r at 10 kilometers. Directive gain is 5 dB and radiating a total power. So radiating power, that is total power radiating is given by 20 kilowatt. 20 kilowatt. Then they are asking what is the electric field intensity E. What is the electric field intensity? We have to calculate. E we have to calculate. So power radiated is given, directive is given, E we have to calculate. But we can define directive gain or D naught directive gain. This is the directive gain. Directive gain or dz also, or dz, d naught or dz. Directive gain is equal to already we defined this definition. What is the definition? What is the formula? 4 pi into radiation intensity by radiation intensity of the antenna by power radiated. Power radiated. But radiation intensity of an antenna is given by r square into average power. R square into average power, or it is also equal to r square into radiation power density. Therefore, directive gain is equal to 4 pi r square into power average by power radiated. Therefore, power average is equal to directive gain into power radiated by 4 pi r square. Directive gain into 4 pi r square. This is in a particular direction. Since here we are multiplying with the dg means it is in a particular direction. The power is in a particular direction. So we know that power average is equal to E square by 2 eta is equal to directive gain into power radiated by 4 pi r square. So if you simplify this, we will get E. Therefore, E square is equal to 2 eta into directive gain power radiated by 4 pi r square. So substitute all the values so that you can directly get. Eta is equal to 120 pi. So 2 into 120 pi into directive gain is 3.162 into power radiated 20 into 10 cube, because 20 kilowatts by 4 pi into r square 10 into 10 cube whole square. So if you calculate and simplify, you will get E is equal to 0.1948 volts per meter. So this type of questions we can expect in the examination. Here they are not asking directly. So with the help of known formulas we have to calculate unknown values. Here they are asking E. Then how we can relate? So here we know that power average is equal to E square by 2 eta. We can relate directive gain and power radiated in terms of average power. So just relate like that and calculate unknown terms. Next topic is very important, effective aperture. Effective aperture and Friis equation. Effective aperture and Friis equation of antenna. So here the effective aperture is defined as the effective aperture indicated with the symbol AE, or it is also called as area of receiving antenna. the effective aperture or area of receiving antenna is defined as AE is equal to PR by P average, where PR is time average power received. Time average power received. P average is, we know, P average is time average power density of the incident wave. Time average power density of the incident wave. It is given by AE is equal to lambda square by 4 pi into directive gain. This is very important relation. Effective aperture of an antenna is given by lambda square by 4 pi into directive gain. Or it is also, we can define AE is equal to lambda square by 4 pi into directivity. This is also correct. Directive gain or directivity. This is effective aperture of the antenna. So the basic physical concept is, suppose if you consider a receiving antenna like this, so only through a particular area of the receiving antenna most of the power will absorbed by the receiving antenna. So that area is effective area. That area is effective area. That is a physical meaning of what is effective area of a receiving antenna. So that's why total power received, average power, total average power received by the antenna to the total average power of the incident wave is defined as effective aperture of the antenna. So it is given by lambda square by 4 pi directivity, which is a very important relation. Suppose this is a transmitter, this is antenna, transmitting antenna, this is a receiving antenna, this is receiving antenna. The transmitting antenna is characterized by AET. So this is the effective aperture of the transmitting antenna. So the effective aperture of the transmitting antenna means the area through which maximum power is transmitted. That is the effective aperture of the transmitting antenna. This is PT, power transmitted. DGT, directivity gain of the transmitter. So transmitter is characterized by these three. Similarly, receiving antenna is characterized by AER, effective aperture of the receiving antenna, power received PR, and directivity gain of the receiving antenna. These two are separated by a distance R. Then according to Friis, scientist name is Friis transmission formula. According to Friis transmission formula, power received by the antenna is given by directivity gain of transmitter into directivity gain of receiver into lambda by 4 pi r whole square into power transmitted, which is very important formula to remember. So the power received is directivity gain of the two antennas, directive gain of transmitter multiplied with the directive gain of receiver by into lambda by 4 pi r whole square into power transmitted. This is known as Friis transmission formula, which is a very important formula.